Hello, everyone. Welcome to another DS3 seminar. This one is the last in our current spring series. I'm really happy to introduce Shaz Qadeer today. Shaz is a former colleague of mine at Microsoft Research who has done foundational work over many years on program verification and concurrency. He's now at Facebook working on DM, a blockchain system, and its programming language called Move, which he's going to tell us more about today. As usual, feel free to ask your questions in the chat, and I'll moderate and forward them to Shaz. Thanks for doing this, Shaz. It's all yours.
Thank you, Nick. Can everybody hear me fine? Nick,
Yeah.
Can you hear me? Okay.
Yes, I can hear you fine.
Okay, all right. Thank you for that introduction. As Nick said, I've been working for the past 2.5 years at Facebook on the DM project and specifically on the Move programming language. So I'll tell you a little bit more about the project, the broad project on which I worked, but most of the talk is going to be focused on Move specific issues. So the background is that Facebook started the Libra blockchain project in 2018. And the Libra team decided that this blockchain should be programmable. So they needed a programming language for it. And that's how Move started. So Libra was eventually renamed to DM, and that language came to be known as Move. Okay, so what is DM? DM is what is now called a permission blockchain. So the history of this terminology is that the original blockchain, Bitcoin, the consensus network was formed from anonymous participants. So the different nodes, compute nodes, they did not know about each other. What is known as a permission blockchain is one in which all the participants, their identities are known at boot time when the blockchain starts. However, there's some flexibility, at least in DM, that these participants are allowed to change dynamically. So this is, gives you a little bit of decentralization because, participants can come and go, but the chain, the blockchain, the network persists. Okay. Each participant in this network of nodes is participating in a consensus protocol, which is based on the model of Byzantine fault tolerance. So the idea is that consensus should be reached on the sequence of commands that is being processed, even if some small fraction of the participants lie or fail. So the consensus organizes the commands that could be sent to any node into an ordered log of commands. And each command is, executes. It's a transaction. It's a piece of code, and the implementation of that command is expressed in the Move programming language. So that's the overall story. Okay. So to instantiate this idea, you need two things. You need a decentralized application that is useful and whose computation is going to be replicated by the consensus network. So by decentralized application, all we mean is that the participants who are sending commands into this application, they are, different organizations. They're not really part of the same organization. Because if they were part of the same organization, you didn't need to do all these complicated things that I'm talking about. So the application in the context of DM is something called the DM payment framework, which I'll have a few slides about it later. Okay, then the second thing you need is that you need a group of participants to run nodes in the consensus network. Notice that it is not required that the set of participants who are sending commands to the useful decentralized application, those people don't have to be exactly the same as the participants who are running nodes in the consensus network. They could be different. In the case of DM, the participants in the consensus network, they are the DM association. So here is a list of the DM association members. You can see that there are many companies of coming from different parts of the sector. So starting from the top here, Andreessen Horowitz is a very well-known venture capital company. Bison Trails is just an infrastructure company. They specialize in running validator nodes. I'm sure you all have heard of Coinbase. It's a wallet exchange. It's a wallet, online wallet. Then Kiowa and Mercy Corps, they are nonprofit organizations. Let's see what else. Novi, this is Facebook, and so on and so forth. Okay, so that was the DM association. Now I want to say a few words about the DM payment framework. So here, you need the. So I'll talk about two things: the state. That is of the system, and the commands. What are the kinds of commands that are updating the state? So the state comprises a collection of accounts, each containing one or more of three kinds of things. So either representation, a digital representation of coins, or permissions to do critical operations. So they are represented also as state, or some metadata about the network membership. So you remember I was telling you about the identity of the nodes in the network. They're known to each other, and that the set of members could change over time. So that's what I'm talking about here. So the network membership is also recorded as part of the state of the DM payment framework. Okay, so then state. So when a command comes in, move. So that command is digitally signed. So the digital signature is required for extra security, and also because if the network membership is changing, it has implications for consensus. So the state is updated by these digitally signed commands implemented in Move that do one of a few different kinds of things. So they can either mint or burn or transfer digital coins from between accounts. They can grant and revoke permissions for critical operations, and they can change network membership. So it's all very, very simple. Okay. So now I want to give you a summary of the results that were achieved using Move, and in the rest of the talk, I will talk about the various components of the Move toolchain. Before I do that, does anybody have any questions about the background and the setup? DM association, DM payment framework, and so on. Okay, I'll continue.
Not so far. I do have a question though. I was just wondering about this. The signatures. You said every request is digitally signed. It's signed by under the keys of who? Like the members of the association?
No. So it depends on the nature. So the members of the association are simply running the nodes. So if, for example, one of those nodes, so let's say that the set of nodes that's participating in the network is changing, then the command for indicating that membership would be signed by the association. But if the command is not about changing the network membership, it's that the command is about let's say minting coins or transferring coins from one account to another, then that command would have to be signed by somebody who has some connection to that account. So for example, if you're transferring from an account A to B, then it would have to be signed by A's key, A's public key. Sorry, A's private key.
Sure. Okay.
Okay. Yeah. Any other question?
Not so far. Do ask your questions in the chat as we go. Shaz has mentioned that he prefers to be interrupted with questions as we go.
Okay. So in the move toolchain, we have a language, and the compiler lowers the source code to bytecode. The bytecode is executed by the move virtual machine. So inside the move virtual machine, there's a bytecode verifier and executor. So the bytecode verifier is there to keep the compiler out of the trusted computing base, so to speak. And we also have a prover to do automated proofs of safety specifications. So I'll talk about each one of these components. The DM payment framework is about 14,000 lines of code, and plus there is 1,000 lines of code of the move standard library. So I've not attempted to separate out code and specifications and comments. So this is all represented in that 14,000 lines of code. The entire toolchain, including the move prover, is deployed in continuous integration. So we treat the code for the DM payment framework no different than the code of the entire DM code base or the entire implementation of Move, which is written in Rust. So it's just like another programming language with its own tool chain. And when people make changes to that code, it goes through the entire tool chain, including the prover. So we were supporting, so over a period of about a year and a half, the system has been operational. It has supported about approximately a dozen contributors, but 4 main contributors. Okay.
Shaz, there's a question. Maybe this slide will answer it. I don't know. But Stephen Coe says, could you tell us more about why the Libra team decided to design and use a new language?
Sure. I think it's because we wanted certain properties. So, so there's many. The answer is not simple. There's many reasons for it. One of them is that from the perspective of the execution environment of a blockchain, it's like programming a database, right? A replicated database. And so you need support for updates for global state. And we felt that using transactions would be a good thing. So you needed transactions. You needed good support for updating global state, and you needed a rather restricted language about which you can do deep reasoning and minimize the possibility for errors. So I suppose you could try to. So what are the options, right? If you take an existing language, then you could try to subset that language. Subsetting often doesn't work by itself. So my experience is that typically you end up with a superset of a subset. And the superset of a subset is enforced by some kind of an extra tool that first makes sure that it is a subset and then also processes the extra stuff, the superset part of it, using annotations and so on. So that's also not that easy to do. And because we were working in a situation where security and correctness was super critical. And we imagine that ultimately we will make the system open so you can have dynamically uploaded code, which should not violate the security and the safety of code that already exists. Because of all those reasons, we just decided to do something clean from scratch. Any follow-up questions? Okay.
No, not right now.
Okay. Yeah, so Move is a language for secure transactional programming. So it, state updates are our first class concern. I typically like to contrast this with the approach in, say, SQL. So SQL is also thought, a language for accessing databases. But I think that SQL is primarily, first and foremost, a query language. And state update is kind of glommed onto it on the side. So here, it's completely flipped. So here we're talking about modeling and update of a global state. That's like the first class concern. And there's not that much attention, at least for now, paid to querying that state. So we have all or nothing semantics for commands. right? And we try as best as we can to support local and automated reasoning. Automated reasoning interpreted broadly, you'll see that we have some fairly advanced things in our bytecode verifier from the point of view of type checking, borrow checking, but we also have automated reasoning of safety specifications based on invariants and reasoning with solvers, logical solvers. The key features of the language include modules, references, and generics. So modules enable us to do local reasoning to some extent. References are very helpful in ergonomic coding, and generics, obvious reasons, lots of code reuse and so on. We don't have dynamic dispatch, we don't have reentrancy. So we like to say that absence of features is a key feature by itself. Okay, any questions? Okay, so let me give you a little bit more intuition about the language by giving you an example. So here's a module, it's called bang. So there's this funny thing in the name of the module, 0xa ... So, everything in Move is based on this kind of an account model. So all global state gets partitioned into accounts, and then there's extensibility in terms of what code is getting executed, and code can get added to the system, and code also gets published into accounts. So 0xa, you can think of it as an account name. It's an account address. So 0xa : bank would be different from 0xb : bank. So it's part of the namespace. So in this module, we have type definitions and function definitions. So there's a type called coin. It just has a single field called val in it, 64-bit unsigned integer. We have functions for creating coins, deleting coins, depositing and withdrawing coins. So a few things to highlight here. So inside create, notice that I have this statement abort unless. So this is checking that the input argument I must be positive. So why is that? Because we are trying to preserve an invariant here that all accounts, all coins that are created, they are non-zero in value. Okay, all accounts that are published inside, all coins that are published in various accounts, they are non-zero in value. The second statement in the create function, move to coin, actually updates the global state by publishing inside address a value of the coin type. Okay, so that's indicated by move to. In the second function, there is delete. There is the converse of it. So move from removes, unpublishes a coin value from the address A. Deposit and withdraw show, another feature, which is the use of references into global state and mutation through those references. So there are two kinds of references: mutable references and immutable references. Deposit takes a mutable reference to the coin that is published in address A, and reference to a reference on the val field, and then increments it by I. So one thing to notice here is that there are in each account you can publish at most one instance of a particular type. So if you need to publish more than one instance of a type, you need to have a container type with a vector inside it or some kind of indexing mechanism, and then you publish the container type in the account. Withdraw is the flip of deposit. So there, of course, we are trying, since we are trying to preserve this invariant that published coin values are all positive, there's an abort unless, and then there is the subtraction, similar to what's going on in deposit.
So okay. Shaz, a couple of questions.
Yeah.
Brian Parno asks on the increment, and I suppose the decrement also, the plus equal I and minus equal I, does it wrap around on overflow?
I think no, it does not wrap around. I think it will do an overflow exception. It will abort.
Okay.
Yeah.
Okay, and another question, the question from me, so in delete, for instance, you do a move from coin A, and A is any address.
Yeah, I know. So these are all I've not mentioned it. So if no coin is found there, that will also abort. So there's actually another primitive which is exists coin, where you can check whether a value of that particular type is published in A or not. So unless there is an invariant that is enforced through some other logic, you will have to test that.
Right.
Does that answer your question?
I see. I think so, yeah. And this also ties to a question from Claudio Russo, who says types must be nominal then.
That is correct. Yes, here the types are nominal. That's correct.
Okay.
Yeah.
And the types must exist at the types have a, they exist at runtime somehow. You need
So I mean that's an interesting thing. What's going on in Move is that the types are being used as an index into this global table of state. So in that sense, they need to exist. But and I think that it may be that we have types. Actually, I don't know what happens inside the VM when the value is published. Is there a type? No, I think a type is not kept in every sub-value. So the type at the top level is known because that's the key. And that allows us to serialize and deserialize data from persistent storage. I think that types of internal values are not kept everywhere.
Okay. Would delete work at a generic type? For instance, can I transfer any, you said you have generics, could delete have a polymorphic type for any type A? I'm going to move the type A from the address little a.
Yeah, so you could have coin. No, sorry. So you can move from, you cannot put a type. So supposing delete had a type parameter T, okay? You can't say move from T.
Okay.
But you can make coin itself parameterized by some type, and then you can say move from coin of T.
Okay.
Yeah. All right. Okay, so all right. So I was claiming that the logic here is going to allow us to prove locally that all published coins have non-zero value. But there is more to it. They are this by from what I have told you so far, I cannot do this local reasoning because I'm implicitly making an assumption, unstated assumption that move to coin and move from coin and all these borrow, global, mute, etc. They are only can be called directly only from code inside this module bank, and that's true. So what we do is we in the type checker we make sure that these critical operations for accessing global state pertinent to a certain type can only be done within the module that declares that type. Okay. All right. So that's very simple modules. The other part that I want to tell you is that what about permission? So here's an example of some access control based on some permission. So if you this is a common pattern. So you can have a permission value which does not have anything inside it, but it's just its presence or absence in an account gives that account some critical permission. So you can put that value permission into an account and you can remove it from an account. So by default, unless there are some special annotations on these types are essentially linear. Type instances are linear values that cannot be copied or dropped. So if you look at this piece of code that I've written here, where I call the get function on an address A, and then the return value is just dropped on the floor, this would be flagged as an error. Let's consider this one. So you get the variable p, and then you copy it into q, and then you put q into some other account. Okay, I guess there's an address missing here in the input, so ignore that typo. So this will also be flagged as an error because we can't copy p to q. Instead, you would have to move p to q, and then you can do whatever you want with it. So by default, values, struct values, not primitive values, are linear. And then you can eliminate linearity, so to speak, piecemeal, by providing these attributes or abilities on types. So they're a little bit like trait markers in Rust. So there's one ability called copy, another ability called drop. If you add both of them to data, then all the code on the left-hand side that you're seeing will become legal. There are other abilities also that are pertinent to what kind of data can get stored inside global storage, but I'm not going to talk about that. Any questions? Okay, so let's talk a little bit about references. So I'm going to show you a sequence of examples that are erroneous, that show erroneous use of references, each of which is going to be rejected by move. So in this example, dangle after move, you have a coin C, and you take a reference, an immutable reference R into it, and then you move C, and then you try to access R. So this would be rejected. This is dangle after return. So here you are returning a reference into a local variable C that was passed in. So this is also illegal because when the function call returns, that value is torn down. So again, it's the reference is dangling. And this one is a little bit more subtle. Dangle after overwrite. So you have a coin C. Q takes a reference to it. Then R extends that reference to the val field inside Q. While R exists, Q is overwritten with something with a fresh value. So this also would be flagged as an error. So it's very similar to the experience that is being provided is somewhat similar to Rust. So there's an explicit notion of ownership that is being enforced on references. So not surprisingly, Move has its own borrow checker. Two borrow checkers. Remember, I was telling you about the compiler and the bytecode verifier. They are two separate pieces of code. There's a borrow checker at the compiler, that provides very helpful, nice error messages and guides the programmer towards a correct program. And then there is a very parsimonious borrow checker in the bytecode verifier that is not trying to be helpful. It's just saying yes or no. But the point is that the borrow checking the guarantees of memory safety are being provided at the bytecode level. So this borrow checker, it does sound modular analysis. So each function is checked separately. There's the formalization of this borrow checker is based on a directed acyclic graph of abstraction of move memory. So one restriction inside move is that references cannot be stored inside structs. So those of you who are familiar with the Rust programming language would know, would realize that Rust is more expressive in that way. So this thing helps us simplify the borrow checker analysis in one way by easily allowing us to impose a DAG abstraction on memory, and the memory is essentially, the real memory is essentially like a forest, because it's just a collection of records, and each record can have sub-records inside it. So the roots of this DAG contain when the analysis is being done on a function. So the roots of this DAG are all the local variables of value types and all the incoming references, and all the non-roots are the local variables containing references. So by tracking these dependencies, the borrow dependencies, we are able to reject programs such as those shown on the left side. Any questions?
Yeah, I'm wondering about at least from my passing knowledge of Rust, it seems like a huge amount of effort was put into the borrow checker to make it informative and precise and so on. What was that experience like trying to replicate some of it in Move? Was it a big investment for you?
It was a big investment for me. It was, I mean, when I started on this, I didn't know all this stuff. So I had to really work hard at it. And the funny thing is that, if I just show you the examples on the left-hand side, it seems very simple. But the problem is that when you have to deal with all the features of the programming language, you have to deal with loops and procedures and arbitrary control flow, and you have to do it at the level of, say, bytecode, which is kind of low level, so you can't take advantage of structural information in your type checker. It starts becoming non-trivial. So there were several iterations of this until we got to a point where we could write at least, the entire DM payment framework and get the job done. We're still not satisfied with what we have. Sometimes there are idiosyncrasies that we wish we could eliminate. There's more work to be done there, for sure.
Okay.
Yeah. Any other questions? Okay. One other point I want to note is that in Move, you have modules, and modules can depend on other modules. So the dependency graph among modules is acyclic. So if M uses N, it means that M is allowed to use types that are declared inside N and call functions that are declared inside N. So we enforce that these dependency graphs are acyclic. So this prevents reentrancy, and it enhances local reasoning about the global state controlled by M. As I was explaining earlier, because state controlled by there's a notion of state controlled by a module. It's essentially all the instances of the types that are declared inside that module. The modules give us a natural partitioning of the entire global state. And because the dependency graph is acyclic, we can be assured that the global state of a module M cannot be changed by outcalls from M. So that helps, both in informal reasoning and in part of. Oh, so on this point, so those of you who follow the, blockchain news from the blockchain ecosystem. So a while ago, there was all these attack reentrancy attacks. So DAO was one of the very famous ones, and those kinds of problems cannot happen in a language like Move because we don't have dynamic dispatch and we don't have reentrancy.
I guess the lack of dynamic dispatch in a way also, so Claudio asked a question. So does that mean Move is first order? I guess the answer is yes.
Yeah, that's right. We don't have function values or function pointers at the moment. I mean, actually, the funny thing is that Move doesn't even have enums right now, let alone function pointers at the moment.
Does that when you say at the moment, does that mean you have?
The thing. What I'm trying to point out is that we try to be very parsimonious in the features we add, because the team is small, and we are very careful about the quality of the implementation, and we were very worried that if we tried to add too many features at the same time, we would compromise the security of the DM payment framework. So many obvious things we have chosen not to do because we had to do so much in such a short amount of time. So even things like enums, which are completely non-controversial, you really have to think hard about what's the right time to add it in terms of team prioritization. That's all I meant.
Yeah, makes sense.
Okay.
There may be a question coming, but go ahead. I'll interrupt you in a minute.
Yeah. Okay, so I was just a few words about the bytecode verifier. I mentioned this point earlier that we wanted to extract the compiler from the TCV. We think that there was good reason to do it. Because the compiler is just trying to be very helpful. It's just providing more functionality, so it's more complicated. The move compiler is close to 30,000 lines of code. The bytecode verifier is only about 5,000 lines of code. So fewer code means fewer bugs, and so on. Also, another advantage of keeping the compiler out of a system which is in which we are imagining open publishing, is that loading code at runtime would be faster. Because if the idea is that people should be, think about the Ethereum model, right? We wanted to be able to support that kind of functionality in the long run, where clients can upload code, and it would be nice if the compiler didn't have to be run at that time when the code is getting loaded into the system. And finally, the obvious thing of being able to support multiple programming languages in the future.
So there's an interesting question, Shaz. Marcus Cooper asks, how does the migration path for a blockchain work with new language features?
Oh, I see. I think that what this question is asking is that as you make changes, so let's say that there was version 1 of the bytecode, and on that version was used to upload some code, and then later on we changed the bytecode format by possibly adding new versions. Then how are we going to continue to run applications that were written according to the previous version? Did I get the question right, Marcus?
Sounds about right to me.
Okay, yeah. So this is actually kind of a hard question. In fact, I had to learn all this myself. So what we have done in the context of move is that the move bytecode format will always be, how should I say it, backward compatible. I don't know whether it's backward compatible or forward, but let me just define what I mean by that. What this means is that there's always a way to interpret or represent the bytecode in version X into the bytecode in version X plus 1. Okay? So this is what allows us to keep running old code even in subsequent versions of the runtime. Okay.
So Marcus, I enabled you to unmute your mic in case you want to follow up on that directly.
Okay, hello.
Yeah, hi.
Hi. So I think in some other blockchains like Tezos, there is a community vote if you add new language features. May I assume that with here, it's the consortium that decides outside of the blockchain to add new language features?
Yeah, so I think that any addition of language features, at least so far, has gone through a process known as the, DIP, DM improvement process. So it gets discussed and feedback is provided from the DM association side and so on and so forth. Yeah.
But it's separate from the blockchain itself, right?
Yeah, it's not, all this stuff is happening through informal communication. It's not like happening by doing voting, etc. on the blockchain.
Okay. Yeah.
Yeah. Okay. So I'm not going to spend too much time on the details here, but I just wanted to say that the move bytecode representation is very close to it's a binary format. So the code is basically a collection of tables, and those tables have pointers into each other. The most complex pieces, of course, the bytecode instructions, which are inside function definition, and that's where a lot of the hard thinking in terms of the type checking and the borrow checking and whatnot go. So the move bytecode operations stack machine, and it's operating on type values. So you should think when you're thinking about the move bytecode, you should be thinking something like .NET bytecode rather than something like WebAssembly. So my understanding about WebAssembly is that the things are sandbox, but you don't have rich types in it. At least that's my understanding. But here, the kind of types that you saw in the move programming language, they structs and so on and so forth, they get put into the bytecode also. So you're actually doing type checking on the bytecode itself. So you have stack machine. So what I mean by stack machine is that when to do an operation, you put the operands on the stack, then you execute the operation that consumes the operands and then pushes the result on the stack, and then you keep going like that. So in addition to the basic operations, you also have these special operations that have a meaning in the blockchain context in terms of global storage, like move to, move from, and so on and so forth. Okay, so the bytecode verifier is organized as many passes, from simple things to more complex things. The simple things set up in variants that the more complex things that follow depend on. So the first thing you check is that all these tables are linked up correctly. Then you start reasoning about the bytecode instructions. So the first thing that is done is that the linear stream of instructions is converted into a control flow graph over basic blocks of contiguous instructions. And there is something called stack safety that is checked. So you want to make sure that an instruction only consumes which was something that was previously produced in a basic block, and nothing is left over at the end. Then you get to more interesting stuff like type safety. So here you have generics and abilities. So the ability checking becomes interesting and a bit sophisticated when it gets combined with the generics, because you have things like constraints, ability constraints, not only on types but also on type parameters. And then in the reference safety, I already alluded to it, that we have this thing called the borrow checker. Any questions? I'm moving to the move prover now. Okay, so now we are getting to the final part of my talk, which is about fairly very deep semantic verification using logical encoding of the operational semantics of move programs. So we can now prove safety specifications and invariants and preconditions, postconditions, those kinds of things. So this is organized. The move prover is its own beast. It's fairly involved and sophisticated, and it's kind of organized in the same spirit as a lot of tools that came out of verification tools that came out of Microsoft research. I mean, in fact, the way I think of it is that what I'm showing you on the slide has the stamp of Microsoft research on it. This is how program verification tools are developed. So what is going on there is that you basically build a tool like that, like a compiler. And the compiler has various phases, and then you're going back and forth. So in between the move code, which is annotated with specifications, and the ultimate reasoning engine, which is an SMT solver, and we use two, Z3 and CVC4, which by the way is now called CVC5. There are many phases. So we have something called the prover object model. Then we go into the Boogie translator that generates Boogie. Boogie is an intermediate modeling language that contains a an encoding of the operational semantics and the specifications. Then you can use the boogie VC generator, and then you have to extract error traces from it and ultimately show the error traces back in terms of feedback on the original move code. One thing that I wanted to point out here that is very interesting is that even though that to the user, it looks as if the annotations are on the source language and we are verifying the source program, what we are actually doing is verifying the bytecode that is generated. So it's the semantics of the bytecode operations against which the move specifications are being verified. Okay, so so what kind of specifications that we can we do? All right. So so specifications are hosted inside modules at various levels. So you can write, the usual specifications on functions such as preconditions, postconditions, modifiers, and there's one other new thing here called abort if. This is to indicate all the situations under which a function aborts with that command that I showed you earlier, which is this abort unless. Right? Yeah. So the semantics of an abort is that it unwinds all the state updates that happen in the course of the current transaction and makes the state pristine. So yeah.
So,
Okay.
I have a question. When would you put something in the requires and when would you put it in an aborts if? Would you, for instance, could you try to forbid aborts by enhancing the requires?
Absolutely, that's the thing. So aborts, what you do is the way I think about requires and ensures is that they are really true invariants. They are something that the code internally preserves, and aborts if is capturing everything that the environment is expected to satisfy, and you are just double checking to make sure that the environment doesn't violate it. So if you, for example, have a stronger requires, then you can have a weaker abort if, for example, and vice versa. Does that answer your question?
Yeah, I think so. So you're not going to try to prevent aborts. Aborts is a legal outcome.
Correct.
Yeah. I have another question about modifiers.
Mm-hmm.
I would have thought that you're in this world with this in this linear typing discipline where the program is essentially functional. Although it can be, because of the linearity, it can be implemented efficiently with in-place updates. But am I mistaken in thinking that from the source programming perspective, I should think of the program as functional?
Yes, but notice that we also have global state. So a lot of this, a lot of these shenanigans are about capturing the updates on global state. So for modifiers, it will be about the global resources and their instances that are published, what modifications are happening to them.
I see. So the modifiers will speak about, and the globals here are things like the addresses that you have around.
Yeah. So the global would be on the right hand side. You see this bullet, global variables. Mm-hmm. So global of X parentheses within that V. This is referring to the value of the global of type X published in the address V.
Okay.
And this could change, and so you need some kind of framing for it.
I see. Okay.
Yeah.
Thanks.
Okay. So in addition to that, we also have invariants. Right? So you can have invariants inside structs, and these invariants would mean that whenever there's a value of this struct X that does not have any mutable references inside it, somehow it is quiescent, then this invariant would hold on it. Then you also have module level invariants. So these invariants are really about the published global state. And the meaning is that, well, when the system is at rest, meaning that no transaction is in flight, this condition will hold. Okay. Now, the expressions that you use in all these specifications, they are very general. So you really have full first order logic with quantifiers. There are primitives such as Booleans, arithmetic, and vectors. So, you can use all those primitive operations, and then you can refer to local variables. And I already explained about how you can refer to published global values, and you have predicates over the presence or absence of global values, like exists. In addition, you can also define your specification functions, and you can reuse them inside specifications to make things more compact. Okay, so let me say a few words about some critical aspects of building a scalable verifier. So framing is key. Okay, and because we have memory and we have mutable references, we have global state, stuff can get updated. And so we have to somehow account for framing. So, we are able to do a much better job than most here in the context of Move, because Move uses references in a fairly restricted way. So there is an ownership discipline, and we don't have, we have a borrow checker, which enforces that ownership discipline. So we are able to exploit the invariants that are provided by the borrow checker in simplifying how we represent memory and updates to it. So just a reminder, memory is tree structured. So it's a record of records, right? And references into memory can only be stored on the stack. So you can't have references inside structs themselves. So this borrow checker, it computes information that allows memory updates to be modeled using copy semantics. So let me explain what I mean by that. By copy semantics, I essentially mean the following. Imagine that you have a tree T1, and there is a reference into a subtree of T1, which is T2. So let's say it was a mutable reference, and some mutation was done through it. So the way you model the mutation is that you say, okay, I'm this operation, this function that is mutating T2, I'll give it a copy of T2. It's okay to do this because I know that that reference has exclusive access to that subtree. Now that operation is going to modify T2 whatever way it wants, and we get T2 prime, and then we copy it back in the same place as T2. So we model modification through this copy in, copy out semantics. So this is for mutable references, and immutable references can just be treated like values. You don't even have to mess with all this because of the guarantees of the borrow checker. So that simplifies things a lot. Okay, so I think I've made all these points before, so I don't think I need to say anything here. Again, let me say about invariants. I don't know how much we can say. So, okay, so I was mentioning that we have local invariants on structs, and we have global module level invariants. Ultimately, all these invariants are compiled into assumes and asserts, and the trick is in figuring out where to put these assumes and asserts and what assumes and asserts to put. So there is this compilation into assumes and asserts has to be justified using a methodology that is sound, and sound meaning that, okay, well, if all the asserts are verified, then the invariant hold at all those places where we are trying to guarantee that they hold, and you should not put any unjustified assume anywhere, things like that. So it gets complicated in the presence of references, and it really needs to be formalized, and well, that's also a work in progress. So just to reiterate on the results, you have about 14,000 lines of code, and you have specifications about, there's a lot of specifications, right, that we proved, and these specifications are about access control and invariance and exceptional behavior, and we add preconditions, postconditions, modified as necessary to scale reasoning. These things have been developed over a period of a year and a half, and many times these specifications and programs have been changed. The two co-evolve, and we keep them up to date because everything is part of continuous integration. If you run the move prover if I run my move prover on my laptop, all the specifications on these 14,000 lines of code I can verify in 30 seconds. So this is, I mean, all I'm saying here is that I understand very well that the kind of verification that I'm describing, the bulk of the work is in writing the specification, understanding the program, writing the program in such a way that it can be verified. So all I'm trying to say here is that the tool is fast enough. When it works well, it's fast enough for interactive development. But there are huge challenges in the usability of the tool. So small changes in programs or specifications lead to timeout. The reason this happens is because we are using very expressive specifications, particularly quantifiers. For scalability reasons, because we are trying to move deep specifications through bodies of code. If you try to move deep specifications, propagate deep specifications across large bodies of code, it doesn't scale. So you have to keep splitting things. That means that you end up summarizing stuff a lot. And sometimes, summarizing internal functions, private functions with the specifications just becomes tedious. I would rather that I just inline those private functions, but I can't do it because of scale reasons, and I have to write some summaries and modifies and whatnot. Finally, modular reasoning about invariants is difficult. I didn't talk about this, but when I write an invariant at a module, I can refer to not just the state that is in that module, but in many cases, states that is outside that module. Become very complicated if you're not careful, because if the invariant in module A is referring to state controlled by B, then B could be called by another module C, right? He's saying conflicting things about the state of B. You got to make sure that, this all makes sense. Okay, stuff is hard.
Yeah, I have a question about that.
Yes.
Does the ownership discipline, which clearly applies to programs, does it? I would have expected it to also apply to invariants in some sense. Or
Yes. So it is true that okay, let me say that. Let me put it this way. If we module invariants, so that a module invariant declared in A only refers to global state that is controlled by A, then everything is trivial. But what happens is that sometimes it's not enough. The specifications that we want to express do not go outside that restriction. Now what do you do?
So what do you do?
So that would be,
okay, fine.
It's like, yeah.
Because I was thinking that part of your life, because you don't have reentrancy and so on, these issues of things like invariants being broken inside of
some go away, but it's like an onion, some go away, but some still remain. What can I say?
Okay.
Yeah, it's hard. Okay, so I think I'm at the end of the talk, and at this point, I can give you some opinions about what I think is really the crux of Move and the applications that it is targeting. You may not be interested in hearing these opinions because these are all just opinions. Or I can just first I should just take questions.
But
yeah.
So what kind of things you mentioned a few things that you prove about, a few classes of things that you prove about this payment framework. Can you give a sense of like what is the main invariant of the payment framework that you prove?
Yeah, so I think that if I had to say that there was one main invariant, it would be about the access control, because the complexity is really in the access control, that the critical operations only can happen only when certain conditions hold. And in fact, I think that we are still working because while we have proved many specifications, sometimes we feel that there are gaps there and we want to improve them, fill those gaps completely. So access control is one category of specifications. Another category of specifications is that, oh yeah, remember that you were asking me about aborts-if versus requires. So sometimes, you need invariants to show that a certain code will not fail. And that can depend on global invariants. So there are, some codes that are processing, data structures for doing various kinds of bookkeeping. And so you need to write invariants to make sure that that code does not fail. I think that the aborts specifications are pretty significant. So we took a lot of effort to write very precise aborts specifications. So not only, so they are precise. We attempt to specify exactly when a piece of code would fail, because we thought that this would be useful in the long run for telling clients when, and for giving good feedback to clients when they're submitting transactions about why the transaction is aborting. Yeah. So those were the three kinds of the specifications that I remember. I must say that I was not particularly involved in the actual proof of the code. Mostly it was other engineers, people who are more interested, who are given the task of implementing the functional requirements of the DM payment framework. So this is actually very satisfying to me that I just worked on the tool, and most of the time that the tool was being used by other engineers who were not part of the prover development.
Yeah, that's nice. Marcus asks, what's the average size of programs being written? How many programs have been deployed to the blockchain?
So this blockchain is not open at the moment. The only thing it has is the DM payment framework. So we anticipated that in the long run, we can open it up once we have the primary use case, the DM payment framework, worked out and operational. But everything has been delayed because even because of regulatory concerns. So we are not operational at the moment. So everything is delayed.
So I have one more follow-up question on your remarks and what you prove about the access control. I'm wondering how you said earlier about how certain operations need to be accompanied by digital signatures with the authority of the person issuing the operation. How do you reflect that into your spec, into your access control specs? Is that, do these, for instance, do the signature checks appear in move code, and do you have to write some invariants about it?
No. So what happens is that it is actually, that's a good question, and this is how should I say it? I think it is baked in. Basically, what happens is that there's a special parameter to the transaction called the signer. This is the identity of the sender of the transaction, and this has special meaning. So sometimes what you do is you write specifications that refer to the value of that signer, and that just you, as a human being, you interpret that specification in a special way. But there is nothing in the logical reasoning that knows about digital signatures and so on.
I see. And so the signature checks happen outside beneath the abstraction of the program.
Yes, that is correct. Yeah, that's correct.
Okay. Claudio Russo asked, so is it fair to characterize Move as somewhere between BTC script and Ethereum for expressivity?
Yeah, I think that would be a fair assessment. Yeah. Yeah, I think so. Although, I mean, I think actually maybe Claudia knows the answer to this. So does Ethereum have generics? I can't hear Claudio.
Yeah, Claudio, maybe you want to speak. Sorry, I'm going to unmute you. Give me a second. You can unmute yourself now, Claudio, if you want. We see you.
Actually, I don't know, to be honest. If it does, it's probably just by erasure, not in the bytecode.
Okay, so yeah, so we have generics, but we don't have dynamic dispatch. I know that Solidity has dynamic dispatch. But I would say, for the most part, I think your assessment is accurate.
So I had another question. You were talking about, extending the bytecode language, and you would allow old contracts or programs, whatever, to continue to run as long as you could translate the old bytecode into the new bytecode.
Yeah.
But I think there's a danger there, right? Because if the new bytecode is more expressive, it actually opens up the old code to attacks that weren't expressible in the old bytecode. Like you get more, in terms of like contextual equivalence, you get more observations that you can make. So.
Oh, I see what you mean. Okay, so to be honest, I have not thought about that.
Okay.
Yeah. Okay.
But maybe if you're reproving the properties, if the properties still continue to hold, they continue to hold. That's fine. I don't know.
I mean, I think that the expectation was that we would not try to reprove. So okay, well, so what we always imagined was that the bytecode verifier would run on every new piece of code that gets uploaded into the system. The move prover, on the other hand, because of its advanced nature, or you might call it like unpredictable nature in terms of timing and time taken and so on, we were not imagining it would be run at the time of done offline by the programmer. Now, so the bytecode verifier only secures a subset of the safety properties that a user might be interested in. So the question I think that you are asking is whether the security properties that were given to some old code can get compromised because of language extensions and the addition of new code. And I don't think I've ever formally thought about that, tried to think about that problem precisely.
So I think a simple example might be, you start out with immutable locations, and then the bytecode adds update. And now the properties that you were assuming would hold just because the original language didn't support mutation are totally broken.
Yeah. I see what you mean. Yeah, it's essentially kind of like this, that, when if the property that you were assuming were based on, this idea that certain things would be enforced on the surrounding environment of the code, but we kind of loosen that in a future version of the bytecode, and then I see it can get compromised. I see what you mean. Okay. Yeah.
All right. Thank you.
Mm-hmm. More questions? At this point, I think we can just have some discussion. What do you say?
Mm-hmm.
Nick?
Sounds good. Yeah, but do share your thoughts. I'm curious to understand what your personal opinions are about where this is going.
Sure. Yeah. So, I mean, as I worked on Move, I realized that Move has actually very little to do with blockchains, or the common perception of blockchains with consensus and cryptocurrencies and things like that. So, for example, the consensus mechanism does not even get reflected at the level at which the Move programmer is thinking. Move programmer is just thinking that, well, I mean, I'm just going to get transactions, some external entity is going to serialize those transactions into a log, and they will just come at this code in some order that I cannot predict. So I better make sure that regardless of how these transactions get interleaved, I leave the system in a safe state. So this is very close to the database programming model, except that state update is first, it's first class, it's front and center. So so I think that the applications, I mean, should we? So I think that if programmable blockchains really become a thing, right, and solve lots of user problems, then that's a rich enough area, and then you can do a lot of work to improve usability, programmability, and address security concerns, and so on and so forth. But if I ignore that area for a second, then and just think about classical application areas where technology like Move, which is basically programming stateful distributed services, where can it be used? So if you look at, for example, stateful applications. So stateful applications are organized around the idea of replicated state machines. So there is some system for fault tolerance reasons, not because of concerns about people lying or cheating, but just because of fault tolerance. So if you are writing distributed applications where there's a clear separation between the infrastructure that creates the application log, the log of commands, and the code that is implementing each command in the log, then that's exactly the same situation that we have in the DM blockchain and with Move. So you can really, if you have that kind of separation anywhere, you can immediately try to apply technology like Move and try to bring all the security, verifiability, ease of programming guarantees over there. Microservices is a little bit harder. So in microservices, what happens is that you have replicated state machines, but these replicated state machines are kind of like split. So there are many of them, right? And they may be communicating with each other. And the applications, towards microservices because of operational reasons, I think. So each microservice is run independently by a small group of engineers, and they communicate with each other. And the most common way is using RPCs. So another way of organizing a network of microservices could be to organize them as replicated state machines that are communicating with each other via logs. And if you do that again, you can generalize Move with the capability that each transaction, or in addition to updating global state, is also sending messages to other microservices. And you can then start reasoning about global state also. So in short, what I'm saying here is that global state and invariants on global state are very important in building distributed stateful applications. And Move is right there. That's what Move is all about. And it may not be exactly what the doctor ordered for all those applications, but it is getting there. And we can take it there. So in this view, I think of blockchain computation as just one kind of a distributed stateful application. And in my personal view is that we are not going to be in a situation where there is one blockchain to rule them all. I think that we will have many blockchains, and there will be need to build applications that communicate with many blockchains, and for a variety of reasons. For scale reasons, because of application-specific nature of blockchain. So for all those reasons, I think there's going to be many of them, and we will need to be able to communicate and collaborate across all those blockchains. And I think that's where things would be exciting.
Right. Yeah. Yeah. That's it. That resonates with me. Actually, that makes good sense. Yeah, actually, it made me think a bit about things, just in the spirit of like just open discussion. Like, makes me wonder about what do you think the connection is between things like Move and, say, a system like Ivy, which also seem to have some of sort of at least similar at some distance. Some form of ability to communicate between state machines. It's limited form of mutable state.
Yeah,
state invariants and prove them using SMT and whatnot.
I think that they are very related. I think that the model inside Ivy is what I call the synchronous reactive model, which is actually very close to what I'm just calling a transactional programming model, because your commands come in, and you essentially kind of like hold a giant lock on the entire global state, and then you kind of like execute a bunch of functions one after another, and and I think that the big problem here is that some things get simplified. So you have basically coarse-grained atomic actions, very large atomic action, which is this entire transaction. Yeah. But the problem of how to organize the invariants into these, because your state is very large and your invariants have to get organized, how to write things in a nice way so that you can get local reasoning. That is kind of a hard problem, and it could be that there are things that we could learn from how Ivy is approaching it. Yeah, I think so. I think that Ivy also has this other angle, which is its own take on how to deal with the problem of quantifiers.
Exactly.
A more disciplined kind. If you stick to a subset of first-order logic, then there's a particular discipline of quantifier instantiation that is complete in the limit and things like that. So I think that's a separate thing, and these two aspects are completely decoupled. You can be inspired by one or the other. You don't have to come together. Yeah.
Right. Yeah. Indeed. Marcus asks, can you also check or prove Leibniz properties?
Not at the moment, but there are folks interested in that.
Claudio asks, what's Ivy? Claudio, Ivy is a program verifier and programming language developed by Ken McMillan and some others. It's similar in yeah. Okay, thanks. I guess that helps. How important is Leibniz for a blockchain where things are expected to finish in a fixed number of steps?
Oh, I see. Well, so I guess you have to prove that things will finish in a fixed number of steps. That's what Leibniz is. Maybe what you're saying is that fixed number of steps is a constant, regardless of data size or number of participants and so on. Indeed, if that is true, then it could be that Leibniz checking becomes simpler. Yeah, it's possible.
But do you have a termination checker as well as part of?
No, we don't have a termination checker. Our loops tend to have very simple termination properties. I think that termination or Leibniz would be harder to reason about when you're talking about a multi-step workflow, like where different participants are submitting transactions one by one, and you're trying to argue that regardless of what an adversary might do in the middle, you will be able to get that workflow to completion. Yeah.
And there's no recursion?
We have recursion. We have recursion.
Have recursion.
We hardly ever use it. I don't think there's even a single instance of using recursion, but it's allowed.
And including mutual recursion among functions in a module?
Yeah, I think so.
Okay. I think Marcus has another question. Right. If things have to finish in n steps, doesn't it then become a safety property?
Oh yeah, you're right about that. I think that's true. That is true. However, it's all at the same time. No. You're right. You're right. I think that's correct. That's correct. If n is independent of the problem size, then you can just encode it as a safety property. But even if it's dependent on the problem size. Sorry. So when is a property really a Leibniz property? Yeah, I'm blanking out. I guess I don't know.
For terminating programs, then it's total correctness as it's Leibniz and safety are the same, right? If a program always terminates establishing some property, then
I mean, let's say that there is a loop. It's just incrementing a counter that goes up to n. So the loop condition is x less than n.
Mm-hmm.
Then I know that it will terminate in n steps. N is not 5 or 6 like that. It's like a symbolic constant. So I think in this case, we cannot convert that into a safety problem, just a reachability problem, I think. In this case, you have to reason about some kind of like a termination, like a measure metric.
Right. I'm saying if you prove your program's terminating, if you have a termination checker, then and you're proving total correctness of your programs, then in this sense, for me, Leibniz and safety coincide, right? But you need a termination checker.
Mm-hmm.
I don't know, maybe I'm missing something, but.
Mm-hmm.
I think Marcus, it may be more efficient if you just speak, actually. Still can unmute, but. Okay. Well, Shaz, thanks for taking the time. It was fun to chat and learn about all this stuff. Appreciate all the questions from the audience as well.
Yep, I'm really glad to get this opportunity to speak to all of you. Thank you so much for attending.
Yeah, and good to see familiar faces all around. It's
All right, bye everybody.
Right, this is the last in our spring series, so we'll take a break from DS3 for a while. Thanks for joining. Bye.
Bye.